Good evening, everyone. I'm Jyoti Sharma, and this is week two live session, and this will be happen from 6 to 8 p.m. Uh, this is my brief introduction. That right now I'm a PhD student in ISER Bhopal. I did my masters from FRI Dehradun, BSc from University of Delhi, and right now I'm PMRF research fellow. So how we will proceed, as we already have talked about this, that I will have a lot of MCQ question and we will try to solve it. So this is kind of win-win situation that we have. So you are highly encouraged to speak, to communicate, so that the learning can be happen in both direction. So this is what we already have gone through last week. So first we started with the introduction, then we talked about the chemical of concern, what different type of chemicals we have, what different classification we can follow. Then the screening water screening parameter that we want for the air quality and for the water quality as well. And then we talked about particulate matter, but somehow in last week we couldn't touch air quality parameter and particulate matter. So first we will try to cover this air quality parameter and particulate matter, and then we will go to week second syllabus, right? But I just want to give you brief introduction what we learned in week one. So we started with the framework, and this framework is that we have source. So source here is just some process. So for example, it is the combustion. So after combustion, we will have some gas, some heavy metal or something. So we can call it as a component or the pollutant. So from the source, the pollutant will go to some compartment, and that compartment, we know that these are the environment compartments, and from that environment compartment there will be some reaction in environment compartment, and then it will go to the receptor through some pathways, and that pathways can be by breathing, by like from skin, by ingestion. So this is how some pollutant may impact on the human being. So this is the framework what we started initially in week one. So this is how we briefly started it. So for example, there is a combustion. After that combustion, some pollutant or some component A will go to the environment, and this environment, maybe this environment is air or water or land, animal, plant, whatever. So we may have different compartment of the environment. There we may have some reaction, some dispersion, dilution. So there are lot of phenomena that can happen in environment compartment, and then after that, going to the environment compartment, it will go to the human through some exposure pathways. And so it can be inhalation, ingestion, and dermal. So this is how we are exposed to some kind of chemical. So this is how we started, right? Then we talked something about the environment compartment. So if it is a soil, either it is a clay soil or sand soil, or it is a silt soil, because different type of soil have different absorption capacity of the pollutant. So it is better to know about it if we want to intervene to control any kind of pollutant exposure to the human being, right? If it is a water, then this water is running in the river or it is in a pond, so it is very important for us to know. Then we talked about air, and then plant, animal, sediments. We also talked about groundwater also. So what different type of chemical characteristics we have in the groundwater. So this we already have learned. So this is just, I'm giving you the brief description within 1 minute, and then we will go to our next topic that we didn't cover yet. Then we started to talk about the chemical of concern. Our chemical of concern can be organic in nature, maybe inorganic in nature. It may be benzene based, or it may be, if it is a benzene based, then we can say that this is the phenyl based. Then we also have some biphenyl, and you know that the solubility of uh, pollutant is decided based on how it is formed, what is that structural formula of this, either it is organic or inorganic. Because if we have organic compound, the solubility of organic compound in the water is very low, and if it is a inorganic, then yes, the solubility is very higher. So for example, if it is a lead or arsenic or mercury, so these are the inorganic things that we have, and the solubility may increase, and that's how the exposure may be higher. So it is again better to learn uh, what different chemical composition we have of the chemical of concern. So this we already have covered. uh, I don't think that this is right now needed. Then we moved to water screening. Then what are different parameter by which we can start uh, to test whether our water is good to drink or not. So we started with the color, turbidity, taste, and so on. uh, and then okay, so we started with the screening, and we tried to cover the physical parameters, and then we are going to the biological parameters that we need to test in the water. And again, I encourage you people to please participate, because um, you can learn more, and I can also learn from you. So it will be better if you are participating. And please don't be hesitate if you are giving wrong or right answer. Anyway, I will try to correct you, right? This was the last question. We last week we were at this question only, which oxidizing agent is used in standard COD test. COD test is the one of the tests that we use to test the quality of water, right? And you people already have given me answer for this, and this answer is potassium dichromate. And so this is what we learned in the last week. And now on, from the next slide, our session will be to know something new, right? Okay, so the first question is, we have theoretical oxygen demand. This is again one test by which we can test whether our the quality of water is good or not. So my question is, how we can define theoretical oxygen demand? And right now you have four options: experimentally measured oxygen demand using microbes, oxygen demand measured by dichromate oxidation, the stoichiometric oxygen required for complete oxidation of organic matter, oxygen demand after 5 days of incubation. So what do you think? What should be the right answer for this? What is this theoretical oxygen demand? Have you heard about this term? This is the one of the test by which we can learn whether our the quality of the water is good or not. Can you try to give me the answer for this? You can write in the chat box A, B, C, D, and you can also communicate, like you can also speak. And even if you didn't hear about this word, then you can also please let me know so that I can explain more about this terminology or test. So what do you think? What do you mean by theoretical oxygen demand? Any answer from your side? Okay, so I give you the hint that whenever we have some organic matter in the water, uh, okay, so I got one response from Manu. I don't know how to pronounce this name, but okay. So Lakshmi gave me C answer, stoichiometric oxygen required for complete combustion of organic matter. And Manu also gave me BOD is also used to check the air quality. Oh, sorry, water quality. Yeah, you are right. So the answer is C. Yeah, I agree with this. So there are difference between this BOD and theoretical oxygen demand, right? So how it is different is that, so first you just need to understand that you have organic matter in the water, and whenever you have organic matter in the water, this is not good thing, right? We need to remove that organic matter from the water. So how we can remove this? So we can either, so organic matter are carbon and hydrogen based, right? So if we are giving oxygen to the organic matter will be convert into CO2 and water. So this is something, you have organic matter and let me use the pen. Okay, so yeah, so if you have any organic matter and so if you are giving oxygen, so what will happen, that organic matter will be converted into CO2 and H2O, right? But the question is, uh, who will use this oxygen? So if the oxygen is being used by microorganism, so the thing is, if microorganism is degrading the organic matter, then this will be known as BOD, right? So BOD is how much oxygen is needed to degrade the organic matter by microorganism. So this is BOD. Theoretical oxygen demand is, if we know the formula of this. So for example, if we know that this is just methane, methane is not right option, but just say if it is a glucose, say 6H12 or 6, right? If it is a glucose, and if we are if we are just calculating how much oxygen we need to degrade it, right, then this will be theoretical oxygen demand, because we are just using the equation, we just know the formula of our organic matter. So let's say if it is a glucose, then based on glucose chemical formula, how much oxygen we need. So this will be your theoretical oxygen demand. And the third one is chemical oxygen demand. We are not knowing the formula, we do not know whether it is a glucose or something else, but we are adding some oxidizing agent. So for example, we are adding potassium dichromate, right? So if we are adding potassium dichromate, a strong oxidizing agent, so that will degrade this organic matter to CO2 and H2O. So then how much oxygen is required to oxidize the organic matter? So this will be the COD. So I think now the difference is clear. Theoretical oxygen demand, COD, and biological oxygen demand, right? And yes, we use both, or we use everything like theoretical, chemical, and biological whenever it is needed to check the quality of the water. So that's how C answer is the right one. So this I already have talked about. This is our total organic carbon. Let's say this is total organic carbon. Then which we can oxidize using some oxidizing agent will become under COD, how much oxygen we need chemically to oxidize the organic matter. And then with the organism, how much oxygen we need, right? So this is how we can classify. Okay, so I think with that explanation, you can tell me the correct sequence of theoretical oxygen demand, COD, and BOD. What do you think? What is the right answer for this? Which one is higher? It is which oxygen demand is higher, by microorganism, by oxidizing agent, or by stoichiometric equation if we are using? So oxygen demand will higher in which of the case? Theoretical, chemical, or BOD? Okay, so I got some response. Mano gave me a C answer. Yeah, you are right. So this is C, because theoretical will be always higher, because whether it is oxidizable or not, this will give you oxygen demand, right? And COD will be more than BOD, because sometime microorganism can only degrade the organic matter that are biodegradable in nature. But if something is non biodegradable, then we need COD. So it means the lowest one is BOD, then COD, and then theoretical oxygen demand, right? Yeah, Lakshmi also gave me C. Yeah. So C is the right answer. Okay, so we have learnt about the chemical of concern. We have learnt about the water parameter, how we can screen, and then we have few question about air pollutant characterization, and then I think we will move to partitioning coefficient, right? Okay, so we are starting with very simple question, and this question is about aerosol. So how you can define the aerosol? Aerosol is a major part of the air pollution, and so we have four option here: a mixture of gases, a dispersion of solid or liquid particles suspended in air, a chemical compound present only in vapor phase, a secondary gaseous pollutant. So I got B response, and yeah. But the next question is, if you are saying that aerosol is the dispersion of solid or liquid, so the first thing is aerosol may be solid or maybe liquid, and that are suspended in the air. But the next question is, what do you mean by dispersion? What's the difference between dispersion and mixture or the solution? Why we are just saying here that it is the dispersion, but not here we are saying that this is the mixture or this is solution? What's the difference between that? Do you want to tell me, or should I tell? Okay, can mix with everything. Uh, this is like a very vague definition actually, that we can mix it with everything. But this is something like dispersion is something heterogeneous in nature, but not homogeneous. If we are talking about mixture or solution, that most of the time these are homogeneous. So, for example, if I'm giving you the example, the gases in the air, right? So we have a lot of gases, either this is nitrogen dioxide or sulfur dioxide, and every gases are in air, right? So this will be the mixture, this will not be the dispersion. And so dispersion is something little different from the mixture. So this is how I think I have one slide by which I think I can um, did I get something yeah. So this you already know. Okay, so this is something that we have mixture are mostly molecular mixing, right? And dispersion are mostly the particle suspension. And if we are talking about the phases, then in the mixture we do not have very different dispersed phases, but in the dispersion we have dispersed plus the continuous phase. But I think from that example, I think you can see the gases in air, or if we have particulate matter in the air, then the mixture is different from the dispersion. And the particle size also matter, right? In the mixture mostly it is molecular to ionic size, right? But if it is a dispersion, then the size is more than or larger than the molecule. So I think this is how we can distinguish between mixture and dispersion. So whenever we are talking about aerosol, then we are talking about dispersion but not the mixture. So can you tell me uh, so okay, if we have aerosol, so aerosol can increase the climate change, or in very specific, if I'm talking about the warming, so aerosol is warming the earth or cooling the earth? If we have aerosols, so aerosols are nothing but some solid or some liquid particle in the atmosphere. So my question is, does aerosol warm the earth or not? Okay, so I got one response, that is both. But again, my question is, in what case it can cause the warming, and in what case it can cool the earth? So yeah, you are right. Aerosol have both the cases. Aerosol can cause the cooling as well as the warming. But in what case it can induce the cooling, and in what case it can induce the warming? Aerosol, and we do have a lot of benefit of aerosol also, but again we also have some problem with the aerosol. So aerosol is the big topic of the research right now. um, how it can how it can cause the cooling, or how it can cause the warming. So if it is a soot particle, or if it is a black in color, so if we have any aerosol that is black in color, so yeah, so if it is a darker particle, then that may cause the warming, right? And if it is a sulfate particle, uh, yeah, so if it is a sulfate particle, mostly it may cause the cooling, right? And the another thing is that based on the water vapor, so because aerosol can give the a platform on which some water can be come and condense, right? For the cloud formation, so whenever there will be some condensation process will be happen, then it can release the energy, right? And that's how it can again is not directly warming the climate, but it is the one factor that can induce the warming, because it is giving the platform for the cloud formation and condensation will release a lot of energy, right? So yeah, aerosol have a lot of role, but keeping here just like that, we are going to the next question anyway. So which of the following is not a criteria air pollutant? And we have four options here: nitrogen oxide, sulfur dioxide, benzene, particulate matter. Okay, so I got C answer, that is benzene. Okay, so first, yeah, the answer is right, that is the benzene. But again, I will ask the same question. But what do you mean by the criteria air pollutant? How we can say that this particular pollutant is the criteria air pollutant, and this particular pollutant is not a criteria air pollutant? Is there a particular definition for this? Actually, when EPA, that is Environment uh, Protection Act, or before that, USA also started EPA. When USA started with enactment of this environment related act, then USA comes with criteria air pollutant. And criteria air pollutant is something, uh, the first which is harmful. um, Particulate matter are air pollutant mostly found in Delhi. Yeah, but my question is how we can define the criteria air pollutant. So what happened is that when such kind of definition came in picture, it was USA that was started to play with such kind of words. And criteria air pollutant is something, we can create some standards. So for example, and beyond that standard if we are going, then that may impact to the human in a bad way, right? So this is how. So criteria air pollutant are something that are harmful to the human after after some concentration, right? So we are having some standard for that pollutant. So if we are having some standard, and beyond that standard, if that particular pollutant is giving the bad impact to the human, that will be known as the criteria air pollutant, right? So this is how it started. But actually in India it is very confusing right now, because we do not have a exact definition for criteria air pollutant. So if you can just see, USA EPA, that is the Environment Protection Agency, start with the criteria pollutant, and here criteria meaning that the concentration of this pollutant in the atmosphere are useful as indicator of overall air quality. And that's how the sources, acceptable concentration and effect of the criteria pollutant are summarized in the table. So here you can see, like this is how USA started uh, with the word criteria, right? So USA have these 5 6 pollutant that has been classified as the criteria. uh, if we are talking about normally criteria pollutant in India, so these are SOx, that is sulfur dioxide, nitrogen dioxide, ozone, carbon monoxide, particulate matters, and hydrocarbons. But yeah, these are criteria pollutant in India, but still we have a lot of standard value for more than these pollutant. We have 12 or 13 pollutant for which we have values beyond that value that will have some bad impact, right? So these are the this is the table that I already have attached here, so you can look at this table later. Anyway, the next question is, which of the following pollutant is a secondary air pollutant? Carbon monoxide, sulfur dioxide, nitrogen dioxide, ozone. And again, the question I will ask is, what is the difference between primary air pollutant and secondary air pollutant? And if you know that definition, then obviously it is very easy to you to know which one is the secondary air pollutant. Yeah, Lakshmi gave me answer D. Yeah, ozone is the right one. Ozone is secondary air pollutant. But what do you mean by secondary air pollutant? How it is different from primary one? Yeah, so I got some explanation that primary directly from stack, yeah, and pollutant that directly enter the atmosphere. So can you give me some example how you can classify, and what do you mean by secondary then? Secondary are obtained from various reaction between them. Yeah, so this is exactly I wanted to say. So for example, if we have combustion, right? So whatever the gas is being released by the combustion will be the primary air pollutant. But uh, it will go to the atmosphere, right? And it will react with another gases that we may already have, or some another primary air pollutant. So this is how the interaction between either with the already present already present gases that we already have, or the reaction between two primary air pollutant will give rise to secondary air pollutant, right? And ozone is that kind of case. So can you tell me what is the precursor for the ozone formation? Which type of primary air pollutant will lead to the production of ozone? How ozone is being formed? Um, CTCs, I didn't. Okay, so you wanted to say CFCs, right? Yeah. Uh, no, no, no. Actually, we are getting confused because, uh, okay, so we have two type of ozone. We have tropospheric ozone and the stratospheric ozone. And if we do have CFCs, then CFCs are mostly leading to the depletion of ozone in the stratosphere, but not in the uh, troposphere. So we can classify our ozone either it is at the stratosphere or in the troposphere, and CFC are mostly leading to the depletion of ozone in the stratosphere. But in the troposphere, uh, I'm talking in the troposphere, there is the formation of ozone. CFCs are depleting the ozone in stratosphere. But my question is, what is leading to the formation of ozone in the troposphere? Because in the troposphere, the presence of ozone is bad for us. The formation of what are the precursor of ozone formation? So mostly it is nitrogen dioxide. So what happen is that most of the time whenever we have vehicular emission, vehicular emission will give rise to NO, nitrogen oxide, right? And then in the atmosphere we have oxygen. So Manu gave me photochemical reaction. Yeah, you're right. So what happened is that after vehicular emission, nitrogen oxide will be released to the atmosphere. In the atmosphere we already have oxygen, and that's how nitrogen dioxide will be formed. Okay. In the sunlight, whenever we have sunlight, then sunlight will break this down into NO plus O, right? So we have oxygen and we have O that are released from destruction of this NO2 to NO, and this is how we have the formation of O3. So, the major culprit for the formation of ozone in the troposphere is nitrogen dioxide, right? So, and after that you will have, like in Delhi, most of the time this is nitrogen dioxide and hydrocarbons. In the hydrocarbon, these are the volatile organic carbon that are the precursor for this ozone formation. And rightly said, this will initiate the photochemical reaction, and that's how the fog like condition in Delhi, the reason is uh, this only, the photochemical reaction. So yeah, D is the right answer. So this you people already know that what do you mean by the primary pollutant and what are the secondary. So in secondary, most of the time this is ozone, sulfuric acid, ammonia, some particulate matters, and nitric acid and allof, right? Okay. So we have one terminology that is BTEX compound, and that may be best classified as inorganic gases, unburnt hydrocarbons, criteria particulate pollutant, oxide of nitrogen. BTEX, I think from because I already have given you the full form of BTEX, I think that full form is giving you the best idea which option may be the right one. Okay, so I got response from Lakshmi, that is B. Actually, this is B only, not A, because the benzene, toluene, ethyl benzene, xylene, these are the example of hydrocarbons. These are organic things, right? These have C and H. These mostly are CH and H compounds, right? And that's how these are mostly, not mostly, but purely organic compound. And organic compound are hydrocarbons or volatile organic compounds. So these are not inorganic gases, right? So in inorganic gases, can you give me some example of inorganic gases? So for example, if it is the NO2 or if it is the SO2, right? Or yeah, if it is the ammonia, then these are the inorganic gases. But whenever you have carbon chain, either it is double bonded or single bonded or in the benzene like structure. If this is the cases, that will be organic matter, and so this btex compound will come under unburnt hydrocarbon. So B is the right answer, not A. Okay, I think this is a very simpler question, but this is how we will go to the advanced one. Particulate matter 10 refers to particulate matter having an aerodynamic diameter exactly equal to 10 micrometer, greater than 10 micrometer, less than or equal to 10 micrometer, less than or equal to 1 micrometer. Yeah, so I got Mano gave me C, Lakshmi also. Yeah. So yes, so whenever we have particulate matter 10, so 10 means equal or less than 10 micrometer. And this is just to give you a brief illustration that how much big that 10 micrometer is. So if it is so this is the human hair, and in human hair the size is mostly 50 to 100 micrometer, and so we can see it with the naked eyes, but like this size, can you see, this size is something less than 10 micrometer, so you can compare it with the human hair. Okay, so the next question is, because as I told you, particulate matter have the size, and you just gave me the answer that this is particulate matter size less than or equal to 10 micrometer, right? So what is this 10 micrometer? So this is diameter, right? And we use the word aerodynamic diameter. So what is the definition of this aerodynamic diameter? So I have four options here. Any particle measured under a microscope, a spherical particle of density 2.65 gram per centimeter cube, an equivalent sphere particle of density 1 gram per centimeter cube with the same settling velocity, and D is a particle with the same geometric diameter. So I get the response from Lakshmi and Mano. Yeah. So you gave me the answer is C, and yes, the answer is C. So why we do need of this aerodynamic diameter? Uh, why? What is the need for this aerodynamic diameter? Any reason, any particular reason why we are using here the particular terminology that is the aerodynamic diameter? Because we have particulate matter that have different size and different density, right? And if we have very irregular shape, right, if we do have very irregular shape, then we will not have like if we have not circular shape, then how we can say it is the diameter, right? So we
लेकिन
need
लाइव इंटरेक्शन कर रहे हैं
aerodynamic.
मुझे आईआईटी हैदराबाद से 8 बजे तक 8 बजे बतला लिए कोई बतला लिए बंद करी था
Someone is saying something.
जो कोर्स का कह रही ने ओकर आज लाइव इंटरेक्शन है अरे तो 5 मिनट हमारे से बतिया लो का सुनो तो लगा
uh, okay, so coming to the next
मिला
question. Sir, can you please mute yourself? Okay, so the next question is, we have Stokes settling velocity of the particle that is attained when which of the following forces become balanced? And I have four options here. Gravitational forces is equal to buoyant force, drag force is equal to buoyant force, gravitation force is equal to drag force plus buoyant force, inertial force is equal to drag force.
भर्ती कहाँ है अच्छा अस्पताल नु हाँ हाँ अच्छा अच्छा हार्ट अटैक
Okay, so Manu gave me answer C, that is the gravitational force is equal to drag force plus buoyant force. Yeah. So exactly this is the case. So the C answer is the right one. So but the thing is, again, what do you mean by settling velocity? The velocity by which we can settle any particulate matter, right? And whenever it is settled down, then it attain one kind of velocity that is known as the terminal velocity, right? And okay, anyway, so the thing is, whenever we are talking about settling velocity or terminal velocity, the one thing is very clear: we do not have any kind of acceleration, right? You people must have learned about acceleration, right? What is acceleration? Very basic, but I'm starting with so what we are gonna do is we're gonna derive this settling velocity, right, using gravitational force is equal to drag force plus buoyant force. But I just want to make you understand why these are equal. So can you tell me what do you mean by acceleration? What do you mean by acceleration? So acceleration, final velocity minus initial velocity by time. Yeah. So acceleration is something when we are having either velocity is increasing or decreasing, right? This is something acceleration, or acceleration is whenever the velocity is increasing with the time. And the opposite to this is, I think, what is that, retardation something, in which velocity is decreasing with the time. So what happen is that if I have some particulate matter here, and if particulate matter will start to settle down, Lakshmi also said that velocity change with time. Yes, this is the acceleration. So we are at this point that we want to understand that this is the particulate matter, and if this particulate matter is settling down, then there is no acceleration. So acceleration will equal to zero. And you can you tell me the formula for this force? Force is equal to ma, right? So if the force is equal to ma, and if we know that acceleration is zero whenever we have terminal velocity, then this means any external force will be zero. So that's how, if this is our particulate matter, and we know that there is the upward force that is happening and the downward force that there is happening. So if it is a downward, then this is the gravitational, and if it is the upward, it can be drag force, and another one is the buoyant force, right? But we understand that force will be equal to zero, because acceleration will be zero whenever it will be settled down, whenever it will attain the terminal velocity, right? So if this is the case, then we have to equal this. So the gravitational force will be equal to drag force plus buoyant force. So this is how we can calculate the terminal velocity, or we can calculate the settling velocity. So this is the basis. So the crux is that acceleration will be zero, force will be zero, and because the force will be zero, the gravitational force will be equal to drag force plus buoyant force. And this is how we can derive the settling velocity. So that's how C answer is the right one. Okay. So, and as I told you, gravitational force is equal to drag force plus buoyant force. So this is known as the Stokes law, right? And the question is again on this Stokes law. So the question is, according to Stokes law, the settling velocity of a small spherical particle in a fluid under laminar flow condition is directly proportional to what? And I have four options here: the square of the particle diameter and the density difference between particle and fluid, the particle surface area only, the viscosity of the fluid, and inverse of gravitational acceleration. What do you think? The settling velocity is directly proportional to what? Okay, so Lakshmi gave me A answer, and Uma also gave me A answer. Yes, the answer is A only. So what it is, that this is the square. So I'm writing here. So this is our settling velocity. Settling velocity is directly proportional to the square of the particle diameter. So this is d square. The density difference between particle and fluid. So what I can say is, this is density. So density of the particle minus density of any fluid, right? So whenever we will have, so this is how, whenever you have high diameter particulate matter. So for example, if it is a dust, right? Dust have high diameter, right? So because it has high diameter, then the settling of this high diameter particulate matter will be, settling velocity will be higher. And that's how, whenever we have particulate matter that are less than or equal to 2.5 micrometer, the settling velocity is very low, right? So so from here you can estimate what can be the settling velocity if if the diameter of any particulate matter is given to you. So I think this is how you can calculate it. Okay, so we were trying to understand that in next in last slide only. So this is the drag force, this is the gravitational force, and our particle will attain some terminal velocity. And this is what I wanted to say you, that with the time the velocity will be the constant. And if velocity is constant, it is, if it is not changing with the time, then acceleration will be zero, right? And that's how we can equate some forces to each other. Okay, so we talked about drag force, right? So the formula for the drag force is 6 pi mu ru. So this you can say v also, because this is the velocity, and here mu is equal to viscosity. So this is the formula for the drag force. And we already know about the force of gravity. This is mg, right? This is mg, but we know that this mass is nothing but what it is. Mass is, we already have know that density is equal to mass upon volume, right? So mass will be equal to density multiplied by volume. And this is what it is here. So this is density and the volume of the sphere, 4 by 3 pi r cube, right? And this is the g. So this is how we are putting the value for force of gravity. We have a full exploration about the drag force and the force of gravity, and then the buoyant force, and then we will equate, and this is how we will come with the settling velocity. So just see here, this is your gravitational force, we already have talked about. This is your buoyant force, and this is your drag force. And if we are equating them, then the last thing that we will get is this one. This is what we want. So whenever we have velocity, velocity is directly proportional to d square. Velocity is directly proportional to the density difference, and velocity is inversely proportional to the viscosity, right? So these are the three things that I think you need to know. Yeah, this is the last formula that I think you need to remember. Okay, so the next question is, particle deviating from air streamline and colliding with the obstacle are deposited mainly due to Brownian diffusion, gravitational settling, inertial impaction, electrostatic attraction. If particle is deviating from air streamline and colliding with the obstacle, then what is the main reason for this? So something, I'm writing here, let's say this is the obstacle and this is the particle, and this particle was moving in the streamline, but it will leave, or it will deviate from the streamline. So this was the streamline, right? But it will deviate and it will collide with the obstacle. So what is the reason for that? What is the principle for that? It is a Brownian diffusion, or it is the gravitational settling, or it is inertial impaction, or it is the electrostatic attraction. What do you think? What is the reason for this? Not A exactly. What about the inertial impaction? So this is something that whenever we are, so this is the particle, and this particle have some weight, right? And this particle is moving in the air streamline, but because the streamline have some direction, but because we also know have some inertia, if something is moving in that direction, that will go into that direction only. So something that we can see whenever for example, if we are riding some bike or scooter and we have high velocity and we need to change the direction, so it is very difficult for us to change the direction, because inertia, what inertia is saying, that we are moving in this direction and we will go to in that direction only. So this is something about inertia. If you are moving in one direction, you will go into that direction, right? And otherwise it will so this is something about inertia. Or if something is moving, then you have to give external force to make it move, right? So this is something inertia. Whatever state it is, the thing want to be in that particular stage only. So the thing is, if we have any particulate matter, so that particulate matter will not want to go in that direction, but it will go directly straight. And whenever it will go directly straight, and it will deposit or it may collide with the obstacle, and this is how it will be deposit, and this is something due to inertial impaction. And that's how the C answer is the right one. Yeah. Okay, so you can see here, this is the case. Whenever you have a particle and you have some streamline, it will not follow that streamline, but it will go straight, and this is how this is known as the inertial impaction. And this sometime, like whenever we have air filter or some kind of filter that we design, we care about this inertial impaction, right? And that's how we engineer that different type of air filters based on such kind of principles. Okay, so I think here you can see okay, no, I think this is different. Okay, which particle property primarily control inertial impaction? Lakshmi say, but A also occur in less proportion. Let me see what is A. So A is the Brownian diffusion. Actually, this is a different case. This is not deviating from the air streamline. I think in the next question it will be cleared in a better way. I will try to explain in a better way, because the next question is based on this only. Okay, which particle property primarily control inertial impaction? Electrical charge, solubility, momentum, and surface tension. We already have talked about this momentum, right? If we have high velocity and if we are moving in one direction, then it is very difficult for us to either stop it or to change the direction, right? Because the body is in inertia. It is in the state of moving straight. It will want to go to the straight only. So this is something known as the momentum, that is the mass into velocity. Whenever you have high mass and high velocity, then most of the time it is very difficult to control the things, right? And that's how most of the accident may happen, because of this momentum. And that's why we say that please do not give a very high speed to your vehicle, because this is just the momentum, right? uh, yeah, so inertial impaction is due to the momentum. Okay, so the next question is, very fine particle that follow streamline closely and deposit due to random motion are governed mainly by. I think Lakshmi, that will give you a nice explanation why the answer was inertial impaction, but not Brownian motion or diffusion. Yeah. So this is C. So here what we learned is that it is following the streamline closely, right? But in inertial, it was not following the streamline. The first thing. And the second thing, here it will deposit due to random motion. The very important thing, it is due to the random motion, but in inertial, it was due to the momentum, right? Because in the Brownian motion, it is a something zigzag like motion it will follow, and that's how it will be deposit to the obstacles. And so this will come under the Brownian motion, but it is not the inertial impaction. So that's how that question was related to the inertial. And this one, whenever it is following that streamline, but it will deposit due to the random motion but not due to the momentum. And that's how the answer here will be Brownian motion but not inertial impaction. I think it is clear. Okay, and this is a little explanation about Brownian motion. So this is random zigzag motion of very small particle. And again, the very big difference between inertial impaction and Brownian motion is that because inertial impaction is due to inertia or maybe due to momentum, right? Whenever you have the mass is very high or velocity is very high, then it will be deposited. But in the Brownian motion, the mass should be very low because it is a very small particle, and that's how it will follow the zigzag motion, right? And so that's how this is again very different from inertial impaction. So Brownian motion is happened in a very small particle that will follow very random zigzag motion caused by continuous collision between gas molecules, right? And this is how this can also lead to the deposition. The next question is deposition of the particle that touch the surface without leaving the streamline due to their finite size is known as inertial impaction, interception, sedimentation, turbulent diffusion. Here the thing is, it is not leaving the streamline, it is in streamline only, but because the particle has large size and because of that size it will collide with the obstacle, and that's how it will be deposited. So what it is? Inertial, interception, sedimentation, turbulent. Yeah, this is B only. So this is interception. So this is something that we have obstacle and we have particle, but that is in big size and it is going in a streamline, but because the size is very big, then it will somehow it will touch to the obstacle, right? And that's how it will be deposited on the obstacle. So this is something known as the interception. So we have learned that we can deposit so this is something that you have a lot of particulate matter in Delhi, right? And if we do have a lot of particulate matter, we need to deposit it, right? And for deposit we have a lot of principle that we already have gone through. It may be inertial, it may be interception, it may be diffusion, that is the Brownian movement, it may be sedimentation. So the thing is, we have a lot of principle by which we can collect that particulate matter from Delhi, right? But um, we have to manufacture, or we have to design the filter, or some technique or instrument or machine in a such a way that we can exploit such kind of principles, right? Okay, so I think this is the last question about the deposition. So we have particle size, we have deposition mechanism, and you have to tell me, out of this A, B, C, D, which one is the right one. We have learned that Brownian diffusion is due to very small size, and because it is in very small size, then it will move. It will be move in a random motion, right? And that's how I think that is the one clue that you may get. Gravitational settling or inertial impaction is maybe because these are directly proportional to the mass. So if we have mass is higher, then then there is the high possibility that particle size is also large. So let me show you. Yeah. So B is the right answer. So if we have particle that the size is more than 10 micrometer, then this is inertial impaction. And also B, and this one is also gravitational settling. So whenever we have the particle size higher, then either it will go under this inertial impaction or the gravitational settling. For this B, the C is the right one, interception. For C, zero point 0.1 to 1 micrometer, this is fifth, electrostatic deposition, and because this is a very finer, so it will go to the Brownian diffusion, and that's how B answer is the right one. We already have learned about this. Diffusion, this is the zigzag. Interception, so this is the because of the size, it is following the streamline, but because of the size it will be collided. Inertial, it will leave the streamline, and go directly to the obstacle. And electrostatic attraction is due to the charges. And one more that we didn't discuss here is yeah, this is another way to see that diffusion, then inertial deposition, interception, and electrostatic. I think I wanted to show you gravitational one, but here it is not. Anyway, so right now the week one is clear. We already have talked about introduction. We have talked about the chemical of concern, water quality and screening, air quality parameter, and particulate matter. If you have any doubt, then you can just let me know. Otherwise, we will go to week two, because week two have very week two is all about very important topic, but the topic is very small. So I think we will able to cover within another like 50 minutes. So if there is any doubt till this week, you can just let me know. Otherwise, we can go further. So, okay. So for the week two, what we will learn, this is physical chemical property of interest, partition constant, soil air partition constant, application example of equilibrium partitioning. So the very this is actually very important. So if we have any kind of pollutant, so if this is the pollutant, and we already have talked about the environmental compartment, it is soil, it is air, it is water, it is plant, it is animal, it is sediment, right? So if we have any contaminant here, so the tendency of this particulate matter to go to the soil or to the water or to the air, so we just want to know the tendency of this pollutant to move and to make some bond, or to be soluble in any of these things, either in soil or in water or in air, because this is how we can estimate the exposure of pollutant to the human being, right? And that's how, this is something known about the partitioning constant we will talk about. Or another thing that we can say, so for example, you have so for example, you have benzene, right? And you know that benzene is carcinogenic in nature. What do you mean by carcinogenic? Can you tell me? Benzene is carcinogenic in nature. So what do you mean by carcinogenic? This is cancer causing. Yeah. So benzene is carcinogenic, means this can cause the cancer. But we want to know where where does this pollutant leave? Either where we can find this benzene, either we can find in soil or in air or in water. So where we can find this benzene, so that we can be ready to reduce the exposure to the benzene. So how we will get to know that? So first we have to understand the affinity or the tendency of this benzene to be soluble in soil, to be soluble in air, or to be soluble in water. So we have to understand that tendency. That's how we can reduce the exposure, right? And that's why it is very important for us to know the tendency of each pollutant, where it will go, where it will stay. It will stay at the soil, it will stay at the air, or it will stay at the water, and that's how we can reduce the exposure. So and we already have talked about benzene, right? Benzene is organic matter, right? Benzene is organic matter, and we know that uh, matter are hydrophobic. What do you mean by hydrophobic? They are not liking the water. So the solubility of benzene to soluble in the water will be very low. It means we will not have benzene concentration in water very much. Okay, so the thing is, we will not get much of the benzene in the water. So the source, or you can say uh, where the benzene will be deposited, it will be either in the soil or in air. So the exposure of this benzene will not come much from the water, because it will be not soluble in water, because the benzene is organic in nature, but we can find in soil or air, right? But how much among the soil and air, uh, which one which one is attracting more to the benzene, either it is soil or air? So we will learn about this. This is very important to reduce the exposure to the human being, and that's how this week 2 is all about this, the chemical or physical property of the interest. So, and this property is nothing but the partitioning coefficient or constant. So the question are related to that only. Okay, so if we have pure compound A, and the aqueous solubility of a pure compound A is best defined as what? And we have four options here. The amount of A dissolved in water before evaporation start. Maximum concentration of A in water at equilibrium with pure A. The concentration of A in water at any given time. The solubility of A in air. Can you tell me the answer for this? We were talking about benzene, right? So we were seeing that solubility of benzene to the air or to the water or to the soil. And this question is all about, we if we have pure compound A, and if we are talking about the aqueous solubility of this, so which may be best defined as what? Lakshmi gave me a B answer. Yeah, I also agree with this. So the aqueous solubility will be defined as uh, so the first thing you have to understand, this is the equilibrium that is being established. Equilibrium is established between pure A and water. If this is the case, then it will be known as the aqueous solubility. So for example, if we are having water and if we are putting sugar or salt in it, and then what will happen, what is the maximum concentration of salt we can put in the water at equilibrium? At equilibrium means, the condition, one condition will be reached in such a way that uh, salt will not be able to dissolve more. So this will be the maximum concentration of, let's say, salt we can dissolve in the water, and when it will reach to the equilibrium, and that's how this will be known as the aqueous solubility. So I have one question, that if we have organic compounds and if we have inorganic compounds, uh, inorganic compound, and if I want to know the aqueous solubility, so which type of compound will have higher aqueous solubility, organic compound or inorganic compound, and why? Aqueous solubility. Okay, so let me give me answer that inorganic compound will have more aqueous solubility as comparison to the organic compound. The next question is why? Aqueous solubility of inorganic compound is obviously higher than the organic compound, but why is this case? Because very simple case is that water is made up of what? H2O. So this is HOH minus, right? So it is ionic in form, right? And most of the time, inorganic compound also have some charge on that, either positive or negative. So it means whenever we have inorganic compound, that will be attracted by either H plus or OH minus. So there is something, there is a great affinity to make the ionic bond with the water ions, and that's how the solubility will be higher. But if we are talking about this organic compound, most of the time they are non-polar, they do not have polarity, they are made up of the covalent bond, right? And because they are made up of the covalent bond, so the solubility will be not very much higher, because organic matter will like the organic matter only to make the bonds. Okay, and that's how organic matter have less solubility in water as comparison to the inorganic one. Okay, so because the word was equilibrium, then you have to understand when the equilibrium will be reached. It means dissolving will be equal to the precipitate out, right? That's how no more dissolve. We can't dissolve more salt into the water, because the precipitation will the undissolved component will also be uh, will also be come out, right? Okay, so can you tell me the unit for this aqueous solubility? So aqueous solubility of the pollutant is most commonly expressed in which unit? Mg per liter, mole meter cube air, Pascal, microgram, meter cube. Can you tell me the unit that we have for the aqueous solubility? So aqueous, just take the example of salt. So we are dissolving the salt into the water. So the unit for the salt divide by the unit of the water. So that's how it will give you the aqueous solubility. Is it clear? So what can be the right answer for this? Uh, no, because it is aqueous, right? This is aqueous, so we are talking about water only. It can't be air. Chaichi Devi gave me A answer, and that is the right one. Lakshmi, I don't know how you got confused, but because it is aqueous, then it is water, right? So this is something. So if we are putting salt into water, right? So this is the concentration of pure A in water. So the aqueous solubility is nothing but the concentration of pure A in water. So this is something because it is the concentration. So concentration means the mass of pure A divided by the volume of water, right? Volume of the water will be, so this is air, right? This can't be answer. Pascal is also related to the vapor pressure. This can't all be the answer. This too can be the answer because this is meter cube and this is liter, and again the mass of pure A either can be milligram or microgram, but most commonly we people use this A1, that is the mg per liter, right? So A will be the right answer. And ppm is not exactly for the aqueous solubility, but ppm we can use for a lot of application, but right now if we are talking about the aqueous solubility, then most of the time we people deal aqueous solubility in mg per liter only, right? So that's how A answer is the right one. Okay. So what we learned is if we are adding any pure substance A in water, that will be known as the aqueous solubility, but equilibrium should be maintained. Only then we will call it as the aqueous solubility. The next question is related to the saturated vapor pressure. So whenever we have pure liquid A and if it is coming in contact with air, and at constant pressure, the saturated vapor pressure will corresponding to what? The partial pressure of A when evaporation stop completely, the equilibrium partial pressure of A in water when liquid A is present, the total pressure of the system, the pressure exerted by air molecules only. What do you think? What is the right answer for this? So again, this is something like that. Uh, the last question was related to what if we are dissolving, let's say, benzene into water, right? And if equilibrium is being maintained, that will be the aqueous solubility. This question is what if we are putting that benzene in the air and then equilibrium will be formed? Then what this condition will be known as? Okay, so Venkatesh and Lakshmi gave me B answer, and yeah, I agree with this. So this is something that the first thing is equilibrium will be established, and equilibrium will be established the partial pressure of A in air when liquid A is present. So what we are talking about is this is again the concentration of pure A in air, right? In air. So again, this because this is the concentration, so this is again mass by volume, right? So the pure A may have some mass. So for example, benzene may have some mass, and air may also have some volume. So it is something like mg per liter we can talk about, and we can also talk about mg per meter cube also. because we can have the volume of the air. Okay, so this is how the unit may be mg per liter or mg per meter cube also, because this is the concentration of pure A in water, sorry, in air, and the equilibrium should be established. So this is something known as the saturated vapor pressure. So A is the right answer. Okay, so here the saturated vapor pressure of the chemical is usually expressed in Pascal per liter, Pascal or mm mercury, kg per meter cube, dimensionless unit. Okay, this is a very tricky question actually. I will say we do not have very exact answer for this, because if we are talking about the exact answer, then exact answer should be Pascal or mercury. But most of the time, as I told you, we people use mg per liter or mg per meter cube. So this question may have multiple answer. Like you can say b may also be right and c also may be right. So don't be much confused about this, because this is uh, this is something, what is the formal way to express the unit, and one is the common way to express the unit. So I think that may give you the problem, but yeah, so B and C both will be right. Okay, so the next question is, you have pure liquid A, okay, and that is kept in the closed container with air, and the saturated vapor pressure of A is, I think this is again the same question, so I'm skipping this. Yeah. Which property of compound A primarily determine its tendency to partition from water to air? Aqueous solubility, molecular weight, density of water, Henry law constant. So as I told you, since this topic we are talking about, I have the one example of benzene, and if I say that where I can find the benzene, in the air or in the water, so there is some coefficient that we must know where it will go. Not A, not A actually. um this is little advanced, but I think you people can learn it very quickly. The answer is no, not C, but this is D. Okay, let me tell you what is the case. Okay, not C. This is D. Let me tell you. If we have component A, or if we have compound A, if we are telling its equilibrium with the water, then this is aqueous solubility, right? If we have this A divided by the volume of air, this will be known as saturated vapor pressure, right? And let's say this is, let me remove this and let me clear. Okay, this is compound A in the water, and because this is the concentration, so what I'm saying, because the concentration is something density, so this is of the density of A in water, and for the water we have symbol A2, right? So this is something A2. For A1 is for the air, so we have any compound A in air, so this is the volume of the air, so this will be rho A1. But this question is its tendency to partition from water to air, so this is something known as K A, and this is 2 1. 2 is water, right? 2 is water, A is air, and this will be equal to rho A2 by rho A1. If this is the case, then this constant is known as Henry law constant. And that's how D answer is the right one. Right? So here, what we are talking about is, oh, we already have pure compound in water, we already have pure compound in air, but where it will go then? What will be the partition? Right? So again, I'm taking one example. We have some benzene in the water and we also have some benzene in the air, but where this equilibrium will be established? So equilibrium will be established because when more of the benzene will go into the air and the less benzene will be in the water, because we are seeing the concentration of pure compound in water divide by the concentration of pure compound in air. And that's how this is known as the Henry law constant, and that's how D answer is the right one. Is it clear? So Henry law constant is known as, and here we are putting the star. So star means equilibrium condition, right? So this is Ka21 will be known as the Henry law constant, and this is nothing but the concentration of pure A in water divided by concentration of pure A in air, and that will be known as the Henry law constant. Is it clear to you right now why this is the D answer but not aqueous solubility? Because aqueous solubility is pure element or pure compound in just water. So A is not the answer. Molecular weight is not the answer. Density is not the answer. D will be the answer. This is not important right now for you. Yeah, okay. So, which parameter and unit best describe the equilibrium partition of the pollutant between air and water? As I already have told you, if there is a partitioning of pollutant between air and water, we already have talked about Ka21, or you can say another one is Ka12. You just need to flip the numerator and denominator. So we have Ka21, Ka12, and uh, you need to tell me the parameter and the unit. So we already have talked about this Ka21 and Ka12. This is Henry law constant, right? But can you tell me the unit for this? What was the unit for this row A1 and row A2? Because we were dividing that, and that's how this will give you this one. So what will be the unit of Henry law constant? Will it be dimensionless or what? So yeah, it will be dimensionless because it is just the ratio. Yes. So rho A1 is mg per liter and rho A2 is also mg per liter, because we have the mass of pure A either in water or in air, and we are having the volume of either air or water, and then we are dividing these two density or the concentration to each other to have Henry law constant. This will be dimensionless. Yeah, Chaichi Devi gave me dimensionless. Yes, you are right. So this will be dimensionless. Okay. So the next question is, these are important, and this will give you brief introduction about where this pollutant will move, either in water or in air. That's why this is a very important topic actually. So if you have two compound, right, A and B, that have identical aqueous solubility, but A has much higher saturated vapor pressure than B. So which statement is correct? A and B will volatilize from water at the same rate. A will partition more strongly into air, B will transfer more readily to air. Vapor pressure has no role once dissolved. If we have two pure compound, A and B, and both have aqueous solubility identical, right? But A has much higher saturated vapor pressure than B, then which one is the right one? Venkatesh gave me answer B, but I'm expecting answer from female participant also. Yeah, B answer is the right one actually. So, uh, um, yeah, sorry. Okay, just let me understand you. So this is Ka, and we learned about this is if we have 2 1, then if this is a 2, then 2 will come up above. So this is 2 upon this is A1, right? And if the case is Ka 1 2, then this will be row A1 and row A2, right? And what we are talking about here is that which statement is correct. So right now, this one is the Henry constant. Let's say this one is the Henry constant. So what will happen if both has identical aqueous solubility? So this portion is same. If this portion is same, and if A has much higher saturated vapor pressure than B, and if this one is the case, okay, so if this one is the higher, then obviously Ka12 will be higher. And what will be the case? Then this means this compound uh, A, this compound A, because this has higher saturated vapor pressure, then this means it will go to the air more readily. Okay, so that's how B is the right answer. Somehow I miscorrected it. So B is the right answer. Mistyped it, sorry. So B is the right answer. So I think this is clear right now. You just need to follow the ratio only. Okay, I think we have more few questions related to that, and that will make the things more clear to you. The next question is, if a pollutant have low aqueous solubility but have higher vapor pressure, will most likely volatile readily, okay, this is okay, now this is different question. Volatile readily into air, accumulate in sediment, remain in groundwater, bind strongly to soil minerals. So I already got the answer from Venkatesh and Lakshmi, and this is A. Yeah, obviously, if it has low aqueous solubility, it means it will not soluble in the water much, right? And if it has high vapor pressure, it means it will go to the air and it will mix with it, and that's how it will be volatile readily into the air, because that pollutant doesn't want to be in water. And that's how, if that doesn't want water, just like benzene, so it will be volatile readily into the air. And that's how this is again very important to know the partition coefficient or partition constants. Okay, so the next question is, which set of property and unit together indicate high mobility from water to air? If some pollutant you have in the water, but what is the chance that it can move from water to air? What should be the property for this? High solubility and low vapor pressure, low solubility and low Henry constant, high vapor pressure plus high Henry constant, high solubility plus high soil adsorption coefficient. If let's say if we have some compound, let's say if we have carbon monoxide, And if we want carbon monoxide to move from water to air, then what property should that carbon monoxide have so that it can move from water to air? If we want that mobility from water to air, it means the solubility should be low in water, right? Solubility should be low and saturated vapor pressure should be higher. Okay, so this is something, high vapor pressure we should have, and high Henry constant. Henry constant, it was what? 1 by 2. 1 was air and 2 was water concentration. uh, Pollutant concentration in air, pollutant concentration in water. And if we have this one higher, then Henry constant will be higher, right? And that's how C is the right answer. I think right now it is clear what we are talking about. Yeah. So uh, the next term what we have is the mass fraction. Mass fraction of pollutant A in solid phase is correctly defined as, so what we already have learned is 1 is equal to air. We have symbols, right? 2 is equal to water. But we also have pure substance in solid also, on solid also. So 3 is solid, right? So what we are saying, for example, benzene can be in air, benzene can be in water, benzene can be in soil, right? Or on the soil or solid. So if this is the case, then if we have benzene mass, so mass of any pure substance, mass of any pure substance, and here we are not using volume, but here we are using the mass of the solid, and this will be known as rho A3, and this will be known as the mass fraction. This will be known as the mass fraction. Venkatesh, not A, because what I'm talking is this is the mass of pure substance divided by the mass of solid. And if it is the mass of solid, then it can't be the volume of solid, right? That's the difference actually. That can make the confusion, but in the denominator, it is not total volume, it is total mass of the solid. And that's how row A3 is different from row A1 and row A2, because row A1 and row A2 had the unit mg per liter, right? Mg per liter. It was mass per volume. But for the row A3, it is mass of the pure substance divided by the mass of the solid. And that's how this is a little different from this row A1 and row A2. Yeah. And that's how C is the right answer. This one. And this row, uh, row A1 is known as saturated vapor pressure, right? This is saturated vapor pressure. Row A2 is known as aqueous solubility, AS. Row A3 is known as mass fraction, or we can also call it as the mass loading, right? And we already have learnt about Ka12, and this Ka12, what was this? Henry law constant. And this was the mixture of air and water. So the concentration of pollutant in air and concentration of pollutant in water. So we have learned 4 terminology right now, right? And yeah, so C answer is the right one. If there is any confusion, you can just let me know. Otherwise, we will go to the next question. Okay. So which of the following quantity is dimensionless? Aqueous solubility, we already have learned about this, right? Saturated vapor pressure, we already have learned about this. Concentration in water, mass fraction. Yeah. So you people are giving me the D answer. Obviously. So mass fraction was the mass of pure substance divided by the mass of the solid. So both, because both was the mass, then the unit will be mass divided by mass, and that's how this will be dimensionless. Right? Yeah. So that's how D answer is the right one. Okay. So at equilibrium, so here it is using S but not rho, so it can be rho. So it is SA2, and this is equilibrium, and we have saturated vapor pressure. Um, this A2, it means it is for water, and saturated vapor pressure, it means this is per air of compound A are both expressed in mg per liter. Which statement is correct? Both are equal. They represent equilibrium with different reference phase. Both represent the same chemical potential. They can be added to obtain total concentration. Not A, not not A. So the thing is, um, yeah, B answer is the right one, because we are having different reference phase. Here we have pollutant in water, here we have pollutant in air, and it doesn't mean that both are same. No, both are not same, but both represent the equilibrium, but equilibrium with different reference phase. Yeah, so that's how B answer is the right one. Okay. Now we are having it is, I think, um fifth terminology. So what we have learned is this is A1. We already have learned about A2. We have learned about row A3. Then we learned about KA21, and this is KA32. So what do you mean by 32 here? So here 3 2 is because we know that 3 is for the solid and 2 is for the water, right? So this is water solid partition coefficient. This is Ka32 for pollutant A, and you have to tell me the right one. So the ratio of concentration of A in air to water, not air. Ratio of mass fraction of A in solid to aqueous concentration of A. So this is solid by water. And ratio of vapor pressure to solubility, ratio of total mass of A in solid to total mass in water. We are not talking about mass here. We are talking about concentration, right? We are not talking about mass. This Ka32 will be the concentration of your pollutant in solid and divide by concentration of your pollutant A in water. So we are not talking about the mass, we are talking about the concentration, and we know that this one is known as the mass fraction. We learned about this, right? That this is the mass fraction or mass loading. And we also know that this A2, rho A2 is nothing but the aqueous concentration, is it? So the answer should be A, but not something else, is it? No, it should not be D, because we are talking about the concentration. We have rho A3 divided by rho A2, right? And rho is nothing but the concentration. And that's how, yeah. So that's how B should be the right answer, but not D. Is it clear why this is the case? So Ka32 is equal to the concentration of pollutant A in solid divided by concentration of pollutant A in water, right? Okay, so can you tell me the definition of then K32? We already have learned what is the unit of solid whenever our pollutant is in solid, then what is the unit? Whenever pollutant is in the water, then what is the unit? We need to just divide it, and that's how we will get it. So K32 is equal to mass fraction upon aqueous solubility, right? So mass fraction was, let's say, mg per a gram or kg, and it was dimensionless, so because it was mass only. And then this is water, uh, so this was mg per liter, right? So this is kg, sorry, mg is cut. What will be the unit? So this unit will be liter by kg, or what? It will be liter by kg, right? This is the mass fraction. We already have talked about the mass fraction. So this is rho A3 divide by rho A2. And this is how C is the right one, is it? Is there any confusion with this? You just let me know. Otherwise, I don't think that there should be any confusion. So the concentration of pollutant A in solid divide by concentration of pollutant A in water. And if we are dividing this, then whatever the unit will be for this K star 32. Yeah. So the C is the right answer, is it? Is it clear why this is C answer but not B or not A? Anyway, okay. So whenever we have, thank you. So whenever we have high value of Ka32, that indicate that pollutant A is highly mobile in groundwater, preferably partition into pore water, strongly sorbed to solid sediment, solid, rapidly volatile to air. Whenever we have Ka32, whenever we have high value of this, what does that mean? Where this pollutant will go? It will, so 3 is solid, right? 3 is solid, 2 is water. And if we have high Ka32, it means that pollutant A will like to go to the solid phase, right? Because Ka32 is equal to rho A3 divide by rho A2. And if we have this one is more, this one can be more if this one is more. It means if we have more pollutant A in solid, then only this Ka32 will be higher, right? It means the pollutant A wants to be in solid compartment, right? And that's how C is the right answer. Yeah. Okay. So if we have what type of compound is most likely to show high water solid partitioning? Highly water soluble inorganic salt, hydrophobic organic compound, volatile organic compounds, dissolved gases. Which one will show high water solid partitioning? Which type of compound will be either moved to water or to the solid and will not be equally in water or in solid? Which type of compound? These are hydrophobic organic compounds. These are hydrophobic because hydrophobic will not like the water, and that's how these will be mostly in the solid environment compartment, right? And that's how the partitioning will be very higher between this water and solid, right? And that's how B answer is the right one. We already have talked about this, right? Yeah. Okay. Very important actually. The another one is the organic carbon normalized partitioning coefficient, KOC. Now we have another term, that is KOC, is defined as ratio of concentration in air to water, ratio of mass of pollutant sorbed per unit organic carbon to aqueous concentration, ratio of total mass in soil to water volume, ratio of vapor pressure to solubility. Okay, so I got answer B and B. Yeah, so this is right. So from where it came from? So this came from this Ka32 only, because we know that if it is a solid, right? And most of the time, this solid is nothing but soil, and the absorption of pollutant A in the soil will depend on organic compound of the soil. We will have more organic compound in the soil, then it will give high affinity to absorb that pollutant A, right? And that's how we have this term KOC. So this is the ratio of mass of pollutant that has been absorbed. So from where it came from actually. So this is something, I think I have next slide. I think I can, not here, but okay, let me understand you. So this is something, if we have K3A2, so this means that you have mass of pollutant A divide by mass of your solid divide by mass of your pollutant A divide by uh, volume of the water, right? But here, what we are seeing here, that this one, mass of your solid, what we can do here, that this is the mass of pollutant A divide by organic carbon of the solid multiply by organic carbon of the solid divide by mass of the solid, because this will be cut together, and this is how this will be the same. But here what we are defined, it is in the term of the KOC or the organic things, and that's how this will be the mass of. So whenever we have mass of the pollutant per unit organic carbon, so this is something M upon OC, and we are, this one is different, right? So the thing is K32 will be equal to M upon OC multiply by 1 by this ml per liter we already have, and multiply by OC by M, right? And this part will be known as KOC. Okay, and so this and this part, because this is organic carbon in the mass, this will be known as FOC, fraction of organic carbon. So K32 will be equal to KOC multiply by FOC, right? So just remember this, K32 is equal to KOC multiply by FOC. I think next question will be based on that only. Yeah. So the parameter FOC represent what? The fraction of organic carbon in soil, fraction of clay mineral, fraction of fine particle in soil, fraction of pore water. Yeah, so I think Chechi has understood already. This FOC was nothing but the mass of the organic matter upon mass of the solid, right? So this was the FOC. So this is the fraction of organic carbon in soil. So yeah, so that's how A is the right answer. I will take for I think 3-4 minutes more. I think then we need to cover this. Okay. Which soil will show high absorption of hydrophobic organic pollutant, assuming the same contaminants? Okay, so you have to tell me, if we have hydrophobic uh, organic pollutant, and which type of soil will absorb more? Sandy soil, clay soil, soil with high organic carbon content, soil with high porosity. We already have learned, right? The absorption is dependent on the organic carbon of the soil. And if we have more organic carbon, then our work is done. So what should be the right answer for this? Hydrophobic organic pollutant will like organic carbon if we have in the soil. Okay, and that's how, if our soil will have high organic carbon content, that will absorb more organic pollutant, right? Yeah, so that's how C is the right answer. This one I think you know already. If we have partition soil water partition coefficient KD, this KD is nothing but Ka32. So we have organic carbon fraction FOC and we have KOC. What is the relation of this? We already have learned this. Which one is the right equation? Is it C? Yeah. So this is C. So this Ka32 will be equal to KOC multiplied by FOC. We already have learned this, right? Yeah, but the thing is, if we are talking about this KOC, the value may be very high, and that's why we people are using log KOC. And if log KOC value is 4, it implies that what? KOC is equal to 4, KOC is equal to 10 raised to power 2, 10 raised to power 4, or 40. Yeah, so this is 40. Not 40, sorry, 10 raised to power 4, because this is log. So this will be 10 raised to power 4, and the answer will be C. We have 3-4 more questions, but I think we can solve this in next week, and then we will go to the next week. I think because the time is up and we need to go for having the dinner. Anyway, so I think we will continue it in week 3. And thank you so much, because I have, I think, 7 or 8 question, but I will also upload this presentation on NPTEL. You can have access it, and you can also try to solve this MQ question by yourself also. So thank you so much. We will continue it on, I think, week 3, right? So thank you so much for being very patient. And again, the time will be from 6 to 8 only. Thank you so much. And have a nice dinner and night. Thank you so much, everyone. So now I think you may go. So thank you.